Hi guys, it's another video, and we are going to be talking about circular motion. This is Engineer Yedi, and circular motion, we believe you have studied one or two things about it in your junior classes. So about this, we have a couple of a lot of things to talk about. As you can see from the slide, according to the slide producer, we have standard properties. We have relationship between linear and angular acceleration with respect to speed. We have to analyze acceleration into the term of cadential and number. Then we have other things that I know we have about four slides here apart from this. So I will manage up and open to lay on what you have learned in early classes, and if not, we are still going to get what we're talking about. So it's the important thing I'm going to touch. There are a lot of things I need to say. So you come with your note and your writing material as well, so that you can actually flow this class. I believe I'm audible. Sorry, I'm a little bit fast, and it's not because I want to be fast, but it's because of I need to cover a lot of things in limited time I'm being given. Always 1.5 hours. So I just want it to be that 1.5 hours and nothing more. So guys, maybe we should start. If you are ready, I am ready. I just want to know if you guys too are actually ready. So let's take a start. Now about starting, we have to talk about the standard properties, which is the first thing about this. Now, when we talk about standard property, we need to talk about, we are talking about circular motion. A good definition we can give to that. Let's manage this slide. We can see right on this slide. So we can say circular motion is defined as a motion of a body along a circular track, That's the first point you can write about properties. And the next thing we can say is that they are of two types. The circular motion are classified into two categories. The first one is called uniform circular motion. And the second one is called, this uniform circular motion is written as UCM. And the second one is called non-uniform circular motion, which we call NUCM. So you keep all these at the back of your mind, please. Very important, because so most part of junior classes and WAHEC and NECO and JAM focus more on the uniform circular motion. That is why most of the time you talk about the features of circular motion. Let's quickly talk about some other features, which I think is also important. You can always keep it in mind that let's take an illustration. For understanding's sake, as usual, you need to understand what you are writing. It's not about you writing or drawing something without understanding. So try to understand what you are writing. And that is the essence of this class. So please, about this, we can just say from here that when a body of a circle starts from the center of a circle, it's having a radius of r, which is the distance from the circle to any part of the circle. It's called the radius. From the center to this point, we have radius. So let's take this as the radius of the circle. We are taking this as radius of circle, and from there we have a radius is r. So if a body is moving with initial speed, we have the speed or velocity as usual, because velocity component is changing, which is what I want to explain. So we have initially the body is moving in this form. Understanding is what matters, my dear student. Body moving along a circle is having initial velocity of v, which is what a vector quantity. So at a point in time, at an instant of time, at a particular point in time, the body chain courses are moving from that point to this point. Now, when it reaches this point, it's still going to move with the same velocity as this course, which is also going to be tangential to the circle. So my point here, my dear student, is what you want to draw. Just make sure you have a good diagram. So now what I'm trying to say now is, well, fine. The direction of this diagram is not going to stay anyway. Is always, this is a new speed direction or velocity direction rather, which is that. So now it has now made an angle which we call theta, or any value of angle you want to use. Now, what you need to keep here is that what I'm trying to draw, normally if I use my hand, it will have been even better, is that the direction of the velocity here is always forming something like a tangent to this. So which is another property you can write about on the standard property that when you are talking about motion of a body along a circular path, the velocities are changing. You can see velocity is changing from one point to another. So I will be very fast in this video because I have a lot of things to talk about, and I'm just giving 1.5 hours to run the video. So by what we have studied, now you don't say in circular motion that velocity is constant. No. So keeping in mind that what velocity of motion, velocity is changing in a circular track. So the velocity is always changing in a circular track. And that is very important for us to keep at the back of our mind. So another thing you can also talk about, which causes a lot of issues with most students, is that the speed. Now, if it is uniform circular motion, UCM, and not the NUCM, we say the speed is constant. And why do we say the speed is constant? Is very simple. We are going to understand this as we progress on in this chapter. The speed in uniform circular motion is constant because the acceleration is zero. So in uniform circular motion, we consider acceleration of a uniform circular motion to be zero. That is for UCM. That is what differentiates uniform circular motion and what non-uniform circular motion has acceleration. That is what non-zero. That is NUCM. So keep it in mind, if somebody asks you the difference between UCM and NUCM, the UCM are those in which they are what the motion of the body is what is not what accelerating. So, and why do we say it is not accelerating? That means it is moving at constant speed. The speed is constant, but there is a change in what in velocity. As you can see along the circular path, the body is moving. At this point now, if the speed is coming, you can see it is always going to come, and it's always going to form what a tangential. It's always like that. So you keep that at the back of your mind. So any point, any part you are drawing, the direction of speed or the direction of velocity is changing from one point to another. So that is that about speed and acceleration. This is only applicable for uniform circular motion, which is required in your syllabus. So you need to keep that, and as speed is constant, acceleration is that is the body is not accelerating because it's moving along a circular path. But for non-uniform circular motion, there is a change in what acceleration, which we are going to talk about when we talk about this tangential and normal acceleration, which I will quickly talk about because of the advanced level students, which I believe is very important. Then again, you can see as the body is moving with different speed, we can say because it is moving, according to this point, it is moving from one point. Let's say the time here is t, then here it is t plus dt as usual. For those who love following my page, you can see that at a particular point in time, it is being displaced. It's forming an arc. You can see this is arc of a circle. Your knowledge of mathematics. So, and it's giving an angle. So we say the first parameter we are going to talk about, because we're talking about standard properties, is that it is moving at different velocity along a circular track. Fine, we have discussed that. And we say the direction of what? The direction of the body. The body is not what? If it is a uniform circular motion, it's not accelerating. That means the direction of the force is acting inward. There must be a force, because if a particle is placed at this point, T1, the particle is having a mass of m. As usual, we are used to this in dynamics. That is why I'm a little bit fast. Then moves from this particular point, gain a velocity of v. Then the body moves to what the final velocity you have here. Now you can say what it is changing in what? In direction. But it's changing in direction, it is changing with respect to an angle, because at each compartment, from here to another point, that's another angle. So this particular angle we call theta is forming something like an arc. Everybody knows this is radius. You also know that distance from here is also radius. So it is like an arc. So the first standard property I will define, which is what we call excuse me, let me first change my ink for understanding sake, is what we call angular displacement, which is very important for students to keep in mind. I hope you have learned about this in your early classes. Angular displacement is what we call the theta that you see there, because it is forming an angle as it's moving from one point to another point. So this angle of arc in which this is moving is now the what? Angular displacement. So we define that, you can say it is the distance covered by a circular motion from its initial position or from its reference point or from its origin, source of origin, or the what we call the distance of a particle from its source of origin. So it has moved from a particular time to another time. The distance covered in this arc here is what we call theta, and it's called angular displacement. So anyhow you want to define it, another person can define it in vector form. Vector from its origin, you know what we call that. So all these things, that is why I keep saying that you have to watch the video in series to have a good knowledge of physics. So position vector, you can say that's it. Position vector of the position vector of a body in a circular circular motion. It's called its angular displacement, or the distance moved by a body with respect to the source of origin is called angular displacement. We can keep a note for us, but I'm not going to be writing everything. That's why you have to be hearing what I'm saying and writing it. But important points I'll help you keep it down. So angular displacement is just what the distance of an object, let me just write it, from the source, or the distance covered by an object, you can put cover there, from the source of origin is called what? The distance covered by an object from the source of origin is called what? It's angular displacement. It is expressed numerically as theta. And if you go by our mathematics without wasting time, my dear student, we can conclude here that what if the distance covered from here to here is s, as in from this particular point to this point, we say the angle it's covered at that point is called the angular displacement, with not as theta. So we can say now this displacement now s is now equals to, as you can see, my dear student, is now equals to the product of what the radius, which is uniform r, I mean small r, multiplied by theta. So we are saying, look at this now, the distance covered here, that is the normal linear distance it has covered, but the angle it makes, the distance of an object from the source of origin is called what? It's angular displacement in a circle, from source of origin in a circle, so that we have a good complete definition. So it's not about derivation alone, it's about having that. So this is the linear distance. Somebody moved from here to to this point. It has covered the distance of this arc. So an angular displacement of of theta. So the relationship between this distance covered for this arc will be the product of the radius and and this that it has covered. So it's an important formula you can keep in mind, because this we are going to use as we move forward under this topic, as x stands for distance, theta stands for angular. S can be displacement. You can also write displacement as well, but it is linear. Linear, the one you talk about in rectilinear motion, as you move from one side to another, whereby that theta is moving from one place. The angular displacement, that is from the source of the position vector of any object from that is moving a distance in a circular motion. This is what we call angular displacement. Another person can make theta sort of formula and say theta equals to s divided by half. They are still talking about it. As you can see, this particular body, as it moves from one place to another, the angle you can say this will be changing. This is another theta. So we can say mostly we say there is a change in the displacement, in the angular displacement. So most of the time in numericals, we take it as the theta, because it's changing with respect to time. As the time is increasing, this velocity is changing, then the displacement. So somebody can just write again, because as we are growing, we are going to be seeing a lot of things. It's equals to r d theta. What is the theta? Still angular, change in angular displacement. So you can also keep this in mind, still the same thing, but you are only telling us that why this theta we are talking about is not uniform. It's changing with respect to a change in velocity. This is the first standard property you have to understand. How to relate, you can see relationship between linear and angular of each of them. So I've started with angular displacement. The next thing we talk about, maybe we shift this one a little bit upward for space. Fine. So I'll just be taking it with respect to what I'm talking about. Fine. I don't want to move to the next slide. Now, in continuation, my dear student, We can take another standard property, which we call angular velocity, Now, we denote that with omega. You might have studied that in your early classes. Omega. Just like you can see here in the circle, sorry about my circle being raw, just for a lot of explanation. Now, the body is moving along a circular path, it's changing velocity, the linear velocity is changing from one point to another. The same thing, because it's what moving along a circle, you can say maybe it's moving this direction. The angle it's covered, you can see with respect the velocity, change in velocity at a particular point in time along the circular track is called angular velocity. Now, we also define that with respect to the linear. So this is one thing we need to keep in mind. So if you define linear speed or linear velocity as a rate of change of distance with time. So the way you define this one too, you don't need to keep cramming too much of things. And just say the rate, the time rate now, the rate of change, the way you define your linear of change of angular displacement, right? Angular displacement with time. The rate of change of angular displacement with time is what we call the angular velocity. So you can keep that at the back of your mind. So it is just like from what I've said, for understanding's sake, we say angular displacement omega is equals to rate of change of angular displacement, angular velocity omega is the rate of change of angular displacement d theta by what? By dt. So this is the way we relate that in terms of definition. Speed, angular linear speed, which you call or velocity. So it's the rate of change of what? Displacement, a bit ds by what? By dt. So this is it. And when it's angular, it's also like that. But here, according to the third part here, we have to be what? Relating both linear and angular. And that is what I'm trying. I'm trying to do the first and the second now to save our time. I'm not going to be proving too much of formula, as you guys don't want too much of proving. Yes, fine, I understand, but you need to understand concept is important. And that is why we try as much as possible to do the ones that are needful because of the nature of the exam, because the exam varies from one point to another. Now, be that as it may, as you can see here, we are saying the rate of change with time. Something is changing from a point of what, at a point of what, at an instant of time. You can also define instantaneous angular velocity. You can even define average angular velocity, the way you do for linear. The only thing here is that you are considering to be angular. I hope you understand what I'm trying to say, my dear students. Excuse me. Now, in continuation, to relate that, you can say, fine, if angular velocity, maybe I should take this one up a little bit first. Where to write one. Wow. So now having this, so guys, I just want us to have enough space for proving a little thing. Now, if somebody asks me to now prove, I can now say, okay, fine. Now that I know that what angular is just the same as linear, the only thing is I'll just put angle in my definition. So simple. So that for me, I can take it, okay, fine. Since angular velocity is the rate of change of angular displacement with time. So I can say, okay, fine, angular velocity is now the linear velocity is rate of change of displacement vector quantity with time. So no problem. Now I want to compare angular and linear. Now what I will do now is I will now come to my formula, which I have here, which I believe you guys can see. So if I'm taking it in this term, I can write as say, okay, this will be V is equals to, what is ds? That is changing this one, is r d theta. I can say r d theta. I'm just substituting s here. Please note that I have over time. I can write it as dt or whatever I want to write it, the way I want to write it. So what I've done here, my dear students, is I've only substituted what is here. Now from here, you don't need to waste your time. Now, what do you have, guys? V is now equals to direct substitution. We don't need to waste time. What is d theta by dt? D theta by dt is what? Omega. R multiplied by omega. This is a very, very important formula you need to keep at the back of them. It's so simple to prove if you know what you are doing. So my point is the relationship between linear and angular speed is linear speed is equals to the radius multiplied by angular speed. It's a linear velocity is equals to the radius multiplied by angular velocity, depending on the nature of the exam. So this formula, whenever I link formula, I always tell you, you keep this at the back of your mind or your formula list notes, which I believe you all have now. You can always keep them. Now, the next point or the next standard properties we are going to define is the one we call the angular acceleration. Angular acceleration. Angular acceleration. And about angular acceleration, we can say, like I said, excuse me, guys, if we consider the way we define our angular velocity, remember, we say our linear acceleration, rate of change of velocity is acceleration. The same thing you define angular acceleration. So you can just say the rate of change of what? Angular velocity. The rate of change of angular velocity. So that means when velocity is changing, we have what? Acceleration. What is angular velocity? So angular acceleration is denoted by what? I need to talk about that things I didn't talk about here. So angular velocity omega is measured in what? Radians per second, which you can write as radians seconds raised to power negative what? Negative 1. It's important because of those our juniors, brothers and sisters that are writing WAEC, SSE. Now, in a nutshell, angular acceleration is carved out from angular velocity. How do we relate angular velocity? We said angular velocity with linear velocity is r omega. So if we remember from our linear velocity formula, we say velocity change in acceleration is rate of change of velocity. So if velocity, I hope students are following. If velocity is acceleration is always given as rate of change of velocity, we call dv by dt. Remember, under our dynamics, I also give you that acceleration is also given as v dv by ds. Remember this one also? So these are the way when we talk about dynamics, when we integrate. So because I am actually having distance now in terms of r, as you can see now, and here I'm not like having a time function. So I would differentiate in respect to v dv by dr, which is also the same thing as acceleration. We have studied this before in dynamics. So if I differentiate, since acceleration is equals to v dv by dt, so angular acceleration will now be equals to from what we have studied. So you can always go by this anytime, any day. It's simple to know for you guys. It will now be angular acceleration will now be differentiating v dv by dr. It will be angular acceleration we write like alpha will now be equals to r omega times omega will give you omega squared. So this is another important formula you have to keep in mind. So angular acceleration is now given as is measuring radians per second square. So we write it as rad s raised to power 2. So keep that at the back of your mind. It's very, very important. You can see what I'm doing. So angular acceleration equals to r equals to, you can see r rod omega square. V is equals to r omega. I've only differentiate with respect to what we have done. B. Then again, if I want to do it with respect to this one, I can also say angular acceleration equals to r times linear acceleration, just like or linear acceleration at the a is equals to the radius times angular acceleration. So this is also applicable in some cases. You might need them. All formulas that I'm listing out here are basic formula, which I believe one way or the other we might apply it in our analysis. Now, to continue this, let's continue in the next slide to talk about other things we need to cover. We've talked about angular displacement, angular velocity, angular acceleration for uniform circular motion. And now let's talk about other things, which is still on the introduction and the relationship according to the slide. So about that, let's quickly move to the next slide. Fine. Now we are on the next slide, and in continuation to what we have talked about, So far, so good. We have learned some basic parameter like angular displacement, which we denote by theta. I hope students are still here. Angular velocity, which we denote by omega, then angular acceleration, which we denote by something like what? Alpha. So these three properties are very important as we are going to do what? Relating it with our linear or rectilinear speed equation because of questions. Now, in our rectilinear motion under dynamics, we have studied, or under kinematics rather, we've studied that the linear motion formula we have studied is for linear motion, V is equals to U plus AT. Remember, V square is equals to U square plus 2AS. S is equals to UT plus half 8 squared. And the last one, S equals to U plus A by 2, that is A over 2, the open bracket 2N minus 1. I hope my students still remember this. We have studied this in kinematics. You can watch the video. These are the equation of motion. And this last one might not be popular. It is just for at an instant of time, at a t time, from what t to t plus dt, you can always use this. For example, at the third seconds of journey. So you understand, it's not that t is equals to 3, or you take n to be 3. We've done examples of this if you follow the sequence from the video series. Now, with respect to what we have here, my dear student, we can now say, from now, you can now substitute the same formula to this. That is the next part. Now here, what is our speed now? It is now omega. Yeah, omega is equals to, you have u plus, what is a? Alpha t. I hope student can complete this. Then you have omega squared. Now what we are, speed of velocity has now changed to angular in circular term. Do you understand that? So omega squared equals to u squared plus 2 alpha theta. What is theta? Angular. So it's just the same formula. Here you can say theta is equals to ut plus half alpha t squared. And the last one can be theta is equals to u plus alpha by 2. We open the brackets 2n minus 1. So this is the equation in what? With respect to linear equation, you also have to keep in mind to solve for what? Some complex questions that might come in terms of what? In terms of what? Rectilinear equation or accelerated what? Motion when the body is accelerated. Then the next point, I think I still need to talk about this direction of 18. I know there are a lot of things you need to learn. You know, some of you have learned a lot from your early classes, but now we just need to understand. I'm just trying to bring everything in that first slide together and talk about that. Now, we said the direction of motion is changing, direction of velocity is changing. Now, we can just write a note as well that to determine the direction of a uniform circular motion, we use the right hand thumb rule. We use the right hand thumb. I hope my students remember this, but I've talked about that under a vector video. You have to watch another. Basis of calculus is the first thing you watch. Vector basis, then you start with introduction to physics, kinematics, dynamics, then you move to this, to go, that's it. So this is the way I expect you to watch it, to have deep understanding, on all these things. Now, to get the direction of a circular motion, you use the right hand thumb rule. To understand that, you can just look at it in this way. I will just quickly talk about two cases. The first case we can take, I believe you guys can see this circle, and the circle is having according to what you can see here, the circle is actually having different dimensions. And I'm going to take, okay, fine, I think the white will do well. So let's take the radius. Looking for something that is going to be okay. So let's say this is the radius. Then we have an object moving from that point to this point. Sorry about that. Having an angular displacement of theta, we've talked about that. And it is going to be measured with respect to the tangent. This is the first speed, the vector quantity, and the second one is now like this. And I told you the velocity is what is changing because the direction are changing. We've talked about that. So that being that, we need to understand that here what we are talking about is that the direction of angular velocity along this path, angular velocity we call omega, is moving in, what do you call this direction? Direction of a clock, clockwise, right? So for clockwise movement, for clockwise turning, please keep this in mind, using the right hand thumb rule. Right hand thumb rule, we need to understand that for clockwise movement, you can always keep this at the back of your mind that this is the direction in which you can calculate direction of velocity. Just place your hand. So I believe you guys are here. I guess I have network issues, but I think I'm back. So if you can hear me, we can proceed from where we stopped. Sorry about that. We can move on. Now we have, yeah, I think you can hear me and the record is still going up. Yes, all classes are recorded for YouTube purposes, for posting on social media for others to read. Now, from here, you can see, I said the velocity, angular velocity is changing in clockwise direction. To know the direction of velocity, we use our right hand thumb rule, which you need to understand. This is my right hand, as you can see. Forget about mirror image. This is my right hand. You understand what I mean by mirror image. My right will be showing like left to you. Don't mind my hand. Now, you are going to place your hand in that direction. For example, if it is anti-clockwise, you can see something, this is anti-clockwise now. The direction of velocity vector is what is pointing what? Upward. So what we are saying is that if it is now clockwise, you can see, look at my hand now. That's why I said we now position the movement of the velocity vector. Look at that. It's moving in clockwise direction. Where is my thumb facing? My thumb is facing downward. So the only note I will just write for you now, you might have understand from what I've explained, is that one, for clockwise is CW. For clockwise movement, the velocity direction is downward. And for anti-clockwise, we write that as ACW. The velocity direction is upward, which is very important. So we keep it in mind at the back of our mind, because most of the examiner loves to ask about the direction of the motion of velocity if it is moving from one point to another. Another important thing I can also talk on this before we move to the next part is for us to understand that if a body is actually moving in a circular path, as you can see, the velocity is changing. But one thing is, at any point in time around the circle, the velocity is always tangential, just like what we've talked. Maybe I should add it to the previous slide under this. Now you can say that what the direction of velocity is always what? Tangential. It's important. Velocity is always tangential, means always from a tangent, always tangential to the circle. At any point in time you look at velocity, it is always lying in form of a horizontal. An horizontal line along a circle, outside the circle is called a tangent. So any point in time within a circle, you have explained that just for notes sake. So you need to keep that in mind. Now, talking about the direction, you can see from what we've said that it's just upward and down is a conventional method we use. But the truth is that the direction of angle might be bigger than each other. So if you are illustrating that, for example, now, if I say angle from this point to this point, which was theta, let's say I said that I'm choosing it to be 60 degrees. And I draw another one just for illustration's sake, from here to here, I said is maybe 120 degrees. You know, they are actually facing the same direction, which is downward. Why is it downward? Because what? It is moving what? Clockwise. If I want to illustrate that in direction length, I will make sure that direction length of 60 is shorter than what? That of what? 120. Do you get what I'm saying? So in terms of diagram, because from experience, I can tell you lot of things. This is for the one of 60-degree direction, and the one of 120 degree, we have a longer length. So I'm trying to say that what the direction is also proportional to the length in what when we are drawing with respect to our what right hand example. Another thing you also keep in mind, which I think I need to talk about still on these basics and all those things in page 1, I want to use just what is slide or 1 or 2 slides to explain them before I go to the next slide. Now, another important thing we can always also keep at the back of our mind. There are lots of things to keep at the back of your mind in physics. You have to just note that. Now, is that when you are measuring this direction that we were talking about, let's say you have something like a concentric circle. What I mean by circle, concentric circle is like a circle inside circle. You have learned that in mathematics class. Then they are now moving. What you need to understand in them is what at the same time, what they are going to cover, the angular velocity they are covering at a point in time will always be the same. But their what linear velocity or speed is not the same. Illustration, you might need it because of experience. From experience, I'm talking from experience, what examiner love to ask. So if you consider this, talking about concentric circle, and another one, a small one, is placed, then both are moving with angular speed of omega. We've talked about that. Now, both are having radius, you know, they have different radius. This one radii and the other one radii. They are both moving in the same direction. They have different velocities, which you know, which is always going to be tangential. Let's say this one is this, and the one of this one is what is this? You know, velocity is always moving something like a tangent on top of a circle. So now, as they are rotating in the same direction, we know the movement of this. I said the direction will be downward. See, look at what I draw here. The arrow should be what? Down. So please, those are literally two mistakes we can make. Nobody is perfect, but when I talk about it, you know, I said downward is a clockwise movement. So arrow should be facing down. So now from here, you can see, yeah, my point is these two bodies they're actually moving with at the same point in time. They are rotating, having the same angular speed or angular velocity, you love to call it, or velocities, as the case may be, but different linear velocity or velocities, which is quite common because we're talking about two bodies. So do you understand this? These are very crucial. They might look as if they are simple, but when you see them in question, you start falling for them. And the reason is because we said the speed is constant for uniform circular motion. Acceleration is what directed towards the center. So which will also lead me to the next point, which I want you to write here. Sorry guys, lot of load. I'm trying to make it short for understanding's sake so that it should not be too long. Now look at this guy. We said for UCM, acceleration is 0. That means body is not accelerating. We've talked about that in the first time, part of the characteristics of circular motion, and the one required in your syllabus. Now, from here, if the body is not accelerating, from dynamics, we have studied that F is equals to ma. Right? Everybody should know this very well. Very famous formula of science in Kingston. Now, about this for vector quantity. Now, if acceleration is 0, what is the final answer for force? Force is also equals to 0. We have to keep this in mind. It's important anytime, any day. So if the force is 0, the body is not accelerating in uniform circular motion. But in non-uniform circular motion, it is non-zero. There's an acceleration. So now there is a particular force. So you can just write for NUCM, important point, for non-uniform circular motion, the force direction is always inward. The force direction is always inward. So this is another thing you need to keep in mind. It's part of those things you can see in question on which of the statement is correct about circular motion. Direction of force is always inward. The force that is responsible for keeping the body at that particular point in time, we call it centripetal force, which is the next thing I'll talk, which will be the last thing in terms of force and acceleration, according to the student slide we are doing. So let's quickly go to another page to talk about that to understand this. Now, my dear students, I'm sorry it's taking too much of our time, but things now we need to know are supposed to be talked about, and there's nothing we can do when it comes to examination. We need to understand or have a deep knowledge about important facts with respect to the syllabus. Now, be that as it may, we can talk about the two types of force required. We call about centripetal force, and the other type of force we call centrifugal force. Now, before we go into this, I'll make it brief. Sorry, I'll make it brief for both A-level and O-level students for us to have both A-level, O-level, and A-level students can watch these videos because I'm going to talk about what is needed. And it's not going to be too much of complexity. Excuse me, I'll break it down in such a way that everybody will get it. Now, from what I'm saying, my dear student, the first point is just for us to know what centripetal force, and to understand that, we might understand that what a force is responsible for keeping body along a circular track. This force we call what? Centripetal force. Now, the whereby centrifugal force is also the force that is responsible to keep the body away from its center. Now, I told you that the direction of force in what? Uniform circular motion is always inward. Now, the force that is responsible to keep that body on track is called centripetal. Remember that keep it away from it is called centrifugal. To understand this, we need to take physical examples and explain with circles and stuff like that, which I think I need to do by one side, out to one side for understanding. So let's quickly do that, not to waste that. I know in early classes we might have studied about all this, and some of us in early classes we don't study about it. It's not a problem. We can still understand all this stuff. Now, what we're talking about, my dear student, is at a point in time. This is the radius of the circle. We've talked about that time and time again. This is the radius. There is a body, we've talked about that, having a mass m directly. These are better, always I've been talking about time and time again. The direction of velocity will be what? Tangential, velocity vector. The body is traveling from one point to another. It's going to have angular displacement of theta. No, time and time again, we keep talking about this. That is physics for you. Now, what we are trying to talk about, there is a force that is responsible to keep this thing from this side. It's moving from this one. I will use my hand because of time. Now, it's now moving from this point to this point, having an angle of theta, the same mass. Now, the velocity is now what's also going to be tangential. This diagram we're going to scale. We know that. Now, the mass, now we say a force is now responsible to keep this particular body in what? In this track along the circular path. That force is now called the centripetal force. So directly numerically, we say the centripetal force is now equal to the mass of the body multiplied by the speed now, which is changing from one point to another. I would say v squared. We are dividing by the radius. Radius is always uniform, and that is why we say by half. So this formula is also very important from junior classes you might have learned. So the force responsible for keeping body inward in a circular track, you can write force responsible. You have to just keep that in the force responsible for keeping a body in a circular track is called the centripetal force. Under the topic of gravitation, you will learn more about it, which is also available on the Academy YouTube page. Now, centripetal force, which is next time you see it, we write it as mv squared by r. So you keep it in mind. That is that about that. Then the other type of force, illustration for that was also important. Now, doing that, my dear student, let's quickly also analyze that. You know, like I said, time and time again, we keep repeating ourselves in physics, and that's what most of my students in classroom love. They want me to keep repeating myself so that they will understand it very well. They love to prove, like I told you, and that is why most of the time you see me proving. They love to prove everything. They said they want to know it exactly the way their teacher would do prove every formula. So, and I loved when students want to know something. So directly now, we are talking about the other type of illustration. Okay, fine. This is the radius. Now, this time, let me use two circles, circle in circle. Sorry about that. Let me use a circle in circle. Another circle. It's just that it's going to take too much of our time, but we just need to do it. So, oh my God, this is not my own circle. Yeah, that should be another circle, not my own circle. So let's make this. The group is not bigger than this time. Let's just illustrate. Oh, I can use one circle too. I just want you guys to get it now. Let's say there is a radius as usual. Let's make it straight. Don't be tired. You don't need to be tired in physics class. Just need to understand that everything is going to be proved. So now that's the radius of your circle. And maybe now there's an object that is placed here. Do it my way for understanding sake. Object is placed here. The object is going to have mass m every time. It's going to have velocity v every time. It doesn't change. So keep it in your mind every time. We use this thing often, always, almost every time, again and again. So now the body is having mass m, like I said, and velocity of v, which is a tangential to the circle. That is the first thing. Now, about this, my dear student, now, here, let's say there is somebody that is now inside this circle. Now, please listen to this. It's very important for students to keep in mind. Now, somebody is now, you're talking about a reference frame now, which we study in kinematics. Now, somebody is now, this thing will move from first point to the other point. Diagram not going to skip this. Tangential is the velocity vector. Tangential is obviously the velocity vector. Now, angular displacement of theta as usual. Now it is moving from this place to this place. Now, if somebody is actually standing here, looking at the body has moved from that particular point to this point. I'm drawing the same body of mass. Has moved from that point to this particular point. Now, along this circular, we said the force responsible for that already discussed the centripetal force. And we say the direction of centripetal force is always acting inward. The centripetal force always acts what? Inward. Inward means what? Inside what? The circle. Centripetal force will act inward. Now look at this, guys. If somebody is now standing here, a reference frame, inside the circle, I said this is Messi now. Messi is standing like this. Messi is the name of one of my students. She's a good girl. Now look at this now. She's standing here and she's now in a rotating flame. She's moving. I don't want to be disturbing myself drawing. You understand? Circle in circle. I just want you guys to see. Now that she's moving inside that thing, as she's moving, dear student, you need to understand one thing. And she's moving in a rotating frame. The velocity is also changing. Mass is also moving. But because she's moving and observing this particular object while she's moving, what Messi is going to see is that the object is what? Stationary. I don't know, maybe you've tried this thing before. You're talking about relative velocity. We have studied that before. Now, because she's in a rotating frame now, as she's moving around this circle, revolving, the velocity of this object is actually changing from another person. Let's say another boy. One of my good students also is standing here. Let's say one boy like that. Let's say AY now is here. Look at AY with his head. Now he's standing here. AY is seeing this body as it is rotated. I'm talking about the object here, moving from one point to another. Can you see? It is rotating from one point to another. So along the circle, which is ray. But because Messi inside here, she's rotating, she will be seeing this body at rest. So that type of situation is what we call what? Now, what Messi will be thinking, oh, as I'm moving from one point to another, the body remains at rest. So now there is a particular force, which I believe you might have studied or whatever. If you want to prove, we're still going to get the same answer. So I'm not going to prove anything that is irrelevant. Nobody will ask you to prove that in our own system of syllabus. Now, here, watch. Now, there will be a particular force that is holding Messi around this circle. As she's changing, she's moving with the circle, revolving around the circle. She's changing velocity, she's changing mass. But she keep on seeing the object that is also changing mass from this view, from the AY view now, changing mass and velocity as being stationary. So what we are trying to say is that what the direction of force now here, there will be what we call a pseudo force. We've talked about that on friction. What I'm saying in a layman's word is that there will be an opposite force now that is keeping this particular thing at equilibrium, at rest. Now, that particular force is now acting away. You know, normally centripetal force is acting inward. Now, the force that is keeping this thing to at equilibrium with respect to Messi that is revolving in a rotating frame now inside a circle, that force now is also equals to what we call what is the same formula, which is what mv squared over r. Please note that that particular force now that is away from the direction of the motion, that is not what that is keeping this body is what is not a real force. Because if we try to draw the free body diagram, which I don't want to go into because of the syllabus, I'm letting myself to what syllabus want you to know. We are going to see that what this particular force now that is keeping the body at equilibrium, which is as a result of what the force that is being generated by Messi. Messi is going to have a weight that is acting downward. Relax yourself, don't be afraid. It's still the same thing. Now, what we are trying to say now is that the weight of Messi is one that generates this force. The force is now away from the circle, not in the direction of what? Of the circle. So that force that keep the body. So and always note that what the weight we always balance. It's always going to this pseudo force. We call it pseudo. Biology students know much about pseudo. Now, pseudo force is not what is not a real force. It's like a fake force. Where we explain now for understanding sake, which keep the body away as a result of what the rotating frame. When the body is observing body in a rotating frame, there is a particular force that keep the body constant or that makes the body to remain stationary when being viewed. So question can come in different way under this. So you need to understand. So question can come in fact, some textbook or test manual will say negative mv squared by r. Then they'll put it in modulo form. Now you should know modulo form, absolute value form, in which we turn to positive. Now, if somebody writes centrifugal force is just can say a pseudo force. That's right. A pseudo force that acts on a body, that acts on a body in a rotating frame, and always balance, and always balance a pseudo force that acts on a body in a rotating frame and always balanced by the weight of the body. So numerically also you can say it is given as F equals to what is always opposite negative mv squared by r in modulo form, which you can write as what mv squared divided by n. So this is very important to you have to keep this in mind because you need to know this in this point. So guys, keep this. I told you students should always have in the back of their mind that there's difference between what we call the speed, the centripetal force, and the centrifugal force. Many students do make mistake from this, but for now, I believe you understand that. And this is why we need to watch this video in series to understand on this. So when the body is in rotating frame, what happened to the what? To the body you are viewing? It is going to be at what? At rest. It's not going to move. And that force generated by the body on the other body is called what? The pseudo force, given as negative mv squared by r. This will cause centrifugal force. That's centrifugal force, which students need to also what? Have at the back of their mind anytime, any day. Now, in continuation to that, now to understand the type of force, because I saw this slide also talk about normal force and tangential force. I need to talk about that too. I just don't need to jump because of time. So the next thing I'll talk about very quickly is what we have also talked about in dynamics. Forces causes what? Change in velocity. I've talked about this before. Now, force is responsible. You can write force is responsible. Force is responsible for a change in velocity. So now the thing about this which you need to know, I've talked about it in dynamics. If you have watched the dynamics video, not kinematic, about forces of nature, forces equation, free body diagram, normal reaction, constraint motion, and the rest. Under my video, you understand what I'm trying to say here. Now, because forces is responsible to change in velocity. Now, there are different type of what? There are two type of force, or which is also responsible for change in acceleration. We've talked about it. From Isaac Newton law of motion, we know that F is equals to what? ma. Remember this? So that means directly we can say force is equals to what is proportional to what? Acceleration. Early classes, you might have studied this in early classes. So the higher the force, the higher the acceleration, where mass remains constant. No problems about that. But according to science, in millisecond of motion, a good illustration, time is not on my side. I'm sorry, my dear student. I'm not jumping, but I believe these are what you might have studied in your early classes. So I hope you have studied them. And if not, just quickly listen to this analysis. You can see this is a block of mass. Every time we talk about block, and we talk about the block having mass m, you understand? Is that a force was applied to the, it's having mass m and having velocity v. Now, if this force is applied to this body, look at this. There is a force that was applied in the direction of the body. It will change the what velocity of this body. Let's say the initial velocity is u, then it will move as because force was applied to it, and it will move from that place to another place and gain velocity. Force is responsible for changing velocity. Simple. So now it is now changing course in the same direction. The force that is responsible for changing velocity in the same direction, you can see only the what? Only the magnitude. Magnitude only is changing. I believe students understand that force is a vector quantity because it can change magnitude and direction. So the force that is responsible for only change, you can see the direction of this block is not changing. Is direction changing? It is because the force is applied under the study of work energy and power. We've talked about this. I have a long way to go in this video. I'm only talking about the first slide, and I've used more than 55 to 60 minutes on this video. Now, but it is important to talk about it because it is what will lead us to the second part for advanced students and for those that are doing UTME and that, because nowadays a question in UTME is unpredictable. Now, here, force acting in the direction of motion that changes only magnitude only. You can see what's a horizontal line? Horizontal line is what? Tangential force. So such force is called what? Tangential. They don't change direction. So only what? Magnitude. Only the size will be changed. Only the position. You understand? They are not changing direction. So we say tangential force. Are you getting it? So now, when we say force is also responsible for changing what? Is that proportional to acceleration? Excuse me. We can say, yeah, the body we accelerate in the same direction in which it is placed. Look at case 2. Look at my force. Now I will use the same diagram. Sorry, it's a little bit dirty, but just manage it. Look at the direction in which I'm pulling the force now. The force is now coming in what? Vertical direction. When something is coming vertical in physics, what do we call it? Normal stress, tangential stress. We've talked about this on the aspect of stress and strain, elasticity. Now, look at this, guys. You can see it is now, the force is now coming in this direction. Because the force is coming in this direction, we say this is the force vector. Now, this one will not only change, look at it, it's coming like this now. As the force, if the force is large, very big force, you understand, very, very big force. If the force is so large, what you see is that what the direction of this thing now, this thing will now start taking a turn. The larger the force, if the force is larger than that, the turning will be sharper. So if the mass is big, you can see if the mass is big, you understand what I'm trying to say? If the mass is so big, we say what the direction, the change in direction of that body will be small. If the mass is what is small, something will quickly take a turn. So now those forces that are responsible for change in direction is called what? Normal force. So what I'm saying in a nutshell is that there are two types of force: tangential force and what? Normal force. For my explanation is never too much, my dear student. Explanation is never too much. So normal force and tangential force. Tangential force is the one that is responsible for changing what? Magnitude only. Whereby normal force is responsible for changing both what? Magnitude and direction. And this is what brings about what you call force to be what? A vector what? A vector. I hope my students are getting that. So this only change magnitude only. So the same thing can also be brought to what? A circular motion. And quickly before, because I don't want to open a new slide. If I open a new slide, there's always going to be what I will talk about. So to avoid talking about another thing, let's quickly finish everything here in this same slide. So by moving this a little bit upward. I hope students are still here. Don't be bored, don't be tired. We still need to understand some other things. So now we can say, because force is responsible for acceleration, the higher the force, the higher the acceleration as discussed. We can now say or conclude as a matter of fact that was acceleration too are also going to be in these two forms. We have tangential acceleration and what? And normal acceleration. So if you view a circle in what? In a 2D form like this, so we can now say, look at it in conclusion or conclusively, that if there is a block of mass m, as usual, my dear student, just to keep you love just having formula at the back of your mind, but when it comes to the concept, you don't like it, you have to like it now. It's important to like it. So now we say, if the force is now being acted like this, we say there are two situations. One is tangential, that is horizontal, and one is normal. That means I have to use a straight line again. Sorry about that. One is tangential force, right? Force, and one is what? Normal force. So what we are trying to say now is that we can now resolve, this is the force acting on the body now. So which is in two forms, tangential and normal. So if the force is acting at an angle of theta, you can just say, you can now say, if it's acting at an angle of theta, you know, this is our opposite. Here will be F cos theta, and here will be what? F sin theta. So a quick one from my dear student to understand is what? Tangential force or tangential acceleration, because force is proportional to acceleration, is given as F sin theta, and this is given as F cos theta. Just for a quick one because of time, F cos theta. So if we go for the magnitude of the two force or two acceleration, you can say the square root, so the magnitude of what? Of the force. We are saying force bring about acceleration. So you can say the magnitude of the force, which is the same as magnitude of the acceleration, will be equals to the square root of what? F sine theta square plus what? F cos theta square. As you know in trigonometry that sine square theta plus cos square theta is equals to 1, then you can continue to bring more relation. So this is the way we visualize acceleration in a circular track. We use this concept, and at the end of the day, because of your time, it's so important for you to know that when we talk about acceleration too, we have tangential acceleration. You have learned that is now given as v squared over r. We keep this in mind because you said the time is fast spent. The normal acceleration an is now given as r omega small. So this is the way we relate these two formulas. I want you guys to keep it. I would love to prove, I would have loved to prove this in a circle, which is very easy for me to do, but because of your time, because of our time, we just need to keep this apart. So both tangential acceleration, normal acceleration is very important in numerical purpose, and the formula is what you need. I think I have actually tried in breaking this thing down for you. So far, so good. You've learned about angular displacement, angular velocity. You've learned about angular acceleration. You've learned about tangential acceleration. You've learned about what normal acceleration. You've learned about how to calculate the direction of a circular motion. You've also learned about what we call centripetal and centrifugal force. As we talk about in a rotating frame, the body is constant along a circle. But another reference frame that is not rotating, we see the body changing. And that is why we say we group it into circular motion and not uniform. So this is just a brief of what I've explained so far. So don't be afraid to face any question numerically when it comes to circular motion. This is the way we do it. And that is the introduction part that my student has prepared for me to do, because he knows this is a very long topic. He only wants me to summarize very quickly. That is why he embedded everything in one slide. So now we move to the next slide, which is a little bit of what is different from what you have learned. So the knowledge of what we've learned here, we are going to use it in this next slide. So we move to the next slide. Wow. Now, about the next slide, we have fine. We have the motion of a pendulum bob, that is the vertical and horizontal oscillation. Now, from early classes, we might have studied about what we call a pendulum bob. And if you don't attend early classes, it's still not a problem, because most of the students online always let me mention that they don't attend early classes or the early classes. It's not that sound, it's not that they are not that sound in helicases. Now, about pendulum block, we can see that this is a pendulum block of length L. Let's take different cases, vertical and horizontal. Let's start with horizontal pendulum bulb for understanding's sake. So horizontal pendulum bulb, you can see what I talked about is now different now from what we are studying. Horizontal bulb. Now for horizontal bulb, I like the diagram he actually brought for us. It will make things easy. It's also at my back. If you are looking at my back behind me, that is a kind of bulb. Now, let's say this is the length of the bulb. The bulb is coming. This is the bulb now, according to what he's trying to let us know. This is the bulb. This is the bulb, as you can see. It's having a length of L. Now, it's being dropped. As it's being dropped, the bulb will move and gain velocity to a particular point. Then when it moves, there will be a particular time when it reaches a particular point, it's going to be rotating. The bulb will go like this. You understand? It will be going, you know this experiment in your helicases. And if you don't know, if you can try to drop the bulb that is what tight on the ceiling, release that particular bulb. You are going to see that the motion of the bulb will be exactly like this. Now, what we are trying to say here now directly, I will take the first thing we need to understand from what you have studied in helicases. We have talked about so far it is now bringing a circular motion. We understand that what there will be a tension, there will be acting. Let's go for what you can see. There will be a tension inside this thing. Everybody knows that. Then remember what we talked about. This is the angle of motion. You can balance to form your triangle. If you are not so good in understanding how we resolve components, you can try and balance your triangle to your own satisfaction for you to see what we are talking about. You understand what I'm saying? So this is just our own way of balancing this. If you have another way of balancing it, for understanding's sake, we are only trying to do it like this. So look at this, guys. This is it. Just trying to show you that the bulb can actually come like that. So not to waste our time, we know we resolve these two components, you know, theta, if that is theta, this will also be theta. Trying to show a straight line here. Look at my hand. I think I need to change the color. Let me just do something, guys. Let me clean that and change the color of that. Maybe to a black so that you can see it. I hope you can see it now. If this is angle is theta, this angle is also theta. But this can be asked to be what to prove is important to know. So sorry about that. So I've taken my marker. So this is also theta. As you can see, so we can prove that in any way. So we can resolve into horizontal and vertical with respect to t. So at this point, with respect to t, this will be t cos theta, because adjacent over hypotenuse is cosine, and the one on the horizontal will be what? T sine theta. As in, I've resolved this into this is horizontal, this is t sine theta, vertical t as in t cos theta. That is what I'm trying to show. And this is t sine theta. As you can see, the direction of angle directly from opposite to hypotenuse. That's sine. Opposite, this is not opposite, this is adjacent to hypotenuse. That is cosine. I hope you understand that. So the weight of the ball will be acting downward. Everybody know the direction of weight. We are not new to this in my class. And what is the force responsible for keeping the body away from the circle? Centrifugal force. What's that? mv squared over what? Over half. So because of the equilibrium we set, you know what we call equilibrium, they will balance out each other. So vertical force will balance. What is vertical force? T cos theta. We balance out the weight. Where is the weight? You can say mg. Just keep it in mind. And the horizontal force was that T sine theta. We balance out what was the force? mv squared over half. So what happened? Dividing the equation 1 by 2, my way, what happened? T gets cancelled out. Cos theta, or you can say 2 by 1 for the right answer. Sin theta divided by cos theta is tan theta is now equals to m also gets cancelled out. We are going to have v squared, or you say v squared r for those that are over r divided by g. So I want to write it as RG. I know my student will say, how did we come about that? So that's why I love taking this step. So tan theta will be equals to, that is v squared over RG. I hope you understand RG here. I also understand RG here. That is when this one comes to time, it will come downward. So you can say the angle at which the pendulum ball will swing for equilibrium tan theta. Theta will now be tan inverse. You say arctan of V squared divided by RG. So this is the important formula students need to keep at the back of their mind for a pendulum bond, because directly we might be using this. And if the question asks for the speed, you can make space for a formula here. The speed can be V is equals to, what happened, my dear student? This is square root. I'm making V squared sort of formula, but if it is, it will be square root of tan theta. You open a bracket, multiply by RG. So these formulas are very important for the speed of a pendulum bulb. This is the way you do it. For the velocity, this is the way you do it. You can also get the tension. Yes, tension is also very important. For the tension also, directly, my dear students, for tension, you can say the tension, to get tension here, what you need to do here is just to take what, you take this one, you make T square formula. You know, T is cancelling out, but here you square both sides. You understand? It will be tension is now equals to square root of cos square theta plus sin square theta into bracket m raised to power 4 d square v raised to power 4 over r squared. You have it. So, or directly, you can just get your tension from this. That is why knowing the formula is quite important. So this is the first part. Another case we can also illustrate in this our above is talking about that means I still have to draw, because I think we have a vertical circular motion, which is important. I've only considered horizontal. Let's talk about vertical circular motion. Circular motion. Of the pendulum ball. This is also very important because of examination of every level. Now, here we can consider the same spring that is being hung or tied up the ceiling. Now we need to be drawing again, or should I just clean this one? And I think I will need to draw, whether I like it or not. I'm only trying to run away from drawing, or whether I like it, I will have to draw. And let me just start with a circle. I'm trying to save our time, but the time says we are not going to save me. I'm going to draw now. So I will draw it. I want to draw it in an oxidation distance for us to see. We only apply some basics of what we have studied in early classes, you know. And I say basics, my dear student. You know what basics mean? I just want us to have something like this. Yes, I will use work energy theorem the way I use in Bernoulli's principle under fluid to explain this. Now, this is the bulb of length L. As you can see, the bulb is having length L. I'm not using length in my other illustration. I just use the tension to balance of everything, which is quite good. The length of the bulb is always from here to there, which I don't use in my notes here. Now, let's say initially the bulb is at this point. Oh my God, I need to change. It's not always easy, my dear students, but you just have to understand. You need to know them to pass your exam very well. All the formula I put in bracket are very important for you to write in your formula. Please write them down. So at this point, we have a bulb of bulb length. The length of the bulb from here to here is the length of the bulb. Please keep that at the back of your mind. Or let's say the length of the bulb is starting from the center to the, just like what we call radius in cent. So this is what it's having initial point as you know, the value of velocity is always going to be tangential. Yes, that's why I said the basis is always needed in everything we are doing. So the speed velocity you write as v vector is having initial mass of m. As it is being drawn from rest, just like what we have here, it will swing. Now let's say it swings from this particular point, changes velocity to, what happened to the velocity? Velocity will be reducing, you know, it will be reducing, yes. Now it moves from that point. This velocity at this point we take as a q vector, which is also tangential. Its initial velocity I'm taking as v, or let's say u, where you want it. Though I'm not going to be using u or v or anything. I will just use what I want to use. You will see what I'm talking about. Excuse me, guys. Now from here, we have this is u. I don't want to change what you've learned in your early classes. You know, u is initial and v is final. That's why I'm changing it to u and v. It doesn't change anything from what I'm not using it in my formula. So, and this is V. So what I'm trying to say is that for this thing has swing from that point to this point, let's say the direction of swing has now moved up. As in, when I released it, it has now swung. You understand? It has swing, or you know your English, from this point to this particular point. And when it does that, what happens, my dear student? You know, there will always be an angle at which it is carried out. We are using our basics. There are different conditions. I will only limit myself to what you have in this level, as I don't want to cause any evil or wreak any havoc. So I will only limit it to what is required. So it has an angular. But look at this, guys. We can now say that, okay, at this point now, it has moved to this point. There is something. We can balance out the height. It has gained a particular height. Guys, are you following? This thing has moved from this point to this point. There's a change in height. Is that also the height? So the height is the height from this point to what? Initial position. So I will bring the height as from here to here. I'll call that place what? Height what? 8, because I want to use work energy theory. Nobody will ask you to prove. Understand? But the formula is quite important in many, many cases, in many, many situations. So this is the height of the ball. Correct. So let me balance this thing as well to have something like a triangle. At this height, this thing has moved from this point. This, my theta is too big. This theta is too big. So don't worry, I will reduce the value of that theta. So for you to see, at this height now, it's forming something like a right angle triangle. This is theta. That theta is too big, like I said. What do we do about that theta? Should we clean it? Or should just leave it like, can you see the theta? Okay, let's clean it. So fine, we have the theta explanation is never too much for you to see. Now, if we consider the length of this thing from here to here is L. Taking place what? The length from here to here, which we call the radius. Some people will do it in terms of, in fact, most of our questions are always coming in terms of radius. So I'm taking it from the center of the circle to this there, my dear student, as radius. Are you there? Can you hear me? Fine. Now I'm taking this as radius. Now, if this is radius, now the total length from here to here is the radius. The height from here to here is what? Is height. What will be the height from here to here? Everything here is radius. Here to here is height. What will be here to here? To be radius minus height. The total length of something is 10. One side of it is 4. What will be the remaining? 6. How do you convert this? 10 minus 4, which is 6. We don't need to rush. Time, I only have 30 minutes more for this video. I think I have one more slide and the example slide, the illustration, which maybe I will leave for you because the time is fast spent. Now from here, but another thing you need to know is that, not that we like complicating things in physics, but we only want to take it because there's an angle of oscillation. It is having an angle. So we can resolve again, my dear student. What do I know? You can see, taking the length, in terms of the length, we can resolve this component. At this point, what's this side? Oh, this is opposite. What's this side? Adjacent. So the total length here, I can take as what? L cos theta, right? From here to here is L cos theta. I hope you understand. Opposite, this is the length, or let's say radius. Should I use radius? Well, in most cases, you see it as length of the bulb. You can take it as radius of the bulb. So let me use length. So length is also the same thing as radius now. So at this point is L cos theta from opposite over this. This is L cos theta. Now, you need to understand something. Like I said, the distance from here to here is h. The distance, this is L minus h, which I'm going to resolve. I hope you understand this because it's quite important for us to understand all these short things. So if this space is L cos theta, so what I want to do now is what I will use my knowledge of mathematics to get the remaining side, which is what I mean. Here to here is L. Here to here is L. Here to here is h. This is L minus h. And from Pythagoras theorem, this L minus h is the same thing as what? L cos theta, from what I have studied, from what I'm trying to prove here. So what I'm trying to say now is that I'm going to use my work energy theorem now. Using work energy theorem. So just listen. At the beginning of this pendulum bulb, it has a mass, and it has a what? Velocity of what? Of u. Are you there? So I can say it gains some kinetic energy to move from this point to this point. So the kinetic energy is what? Half mu squared initially. I hope students are following, and that is why I want to use a v. It doesn't change anything. So it has moved from this point to this point. It has gained some height. That means what we can talk about what potential energy has been overcome. And the potential energy is doing work. And the type of work it's doing is negative work. Why is it negative work, my dear student? What's the direction of the weight? Weight is downward. Then something is going upward. So we say negative of the potential energy. What is potential energy formula? mgh. Now, what is my h now, my dear student? My h can be written as a my h can be written in terms of L. I'm using L, open bracket, 1 minus cos theta. I said that means my h is given as what? 1 minus what? L into bracket 1 minus cos theta. That is my h. As in h is equals to L minus L cos theta. So which I factorize to be L into bracket 1 minus cos theta. How did I come about that? I told you at this point, this is we said the remaining length from here to here is L minus H. And when I resolve this into the component, I get it as L cos theta. So L minus L cos theta. That is how I come about it. I'm trying to let you see it. So I call this place L cos theta. And the remaining height from this point to this point, which is my height, is L minus what? L cos theta. I've resolved this point to component and it was L cos theta. So the remaining point here is L minus L cos theta. So which is what I have as the remaining component. And L minus L cos theta will give me the height. L minus L cos theta will give me the height, which is what I'm using. But I'm only considering the height from this particular point to this particular point. H is equals to L minus L. What is L? The total length from here to down. And what is L cos theta? I'm only considering the remaining part, this place in terms of what? In terms of L, in terms of trigonometry. So you can keep it at the back of your mind. So directly you can just bring out what you need. M will get cancelled out. And if M gets cancelled out, you can say bringing V. Most times we use V. That is why I don't want to use U. So if you use the value of your from work energy theorem, half mv squared from mdu sin theta, then the final kinetic energy, I didn't finish my work energy theorem. Now, the final kinetic energy at this point, what is kinetic energy? Half mv squared. Let me come again, guys. It started from this point, it moves. So initial kinetic energy is half mu squared. It has gained what? It is working what against gravity, gain some potential energy which has been what turned to work done, and we say negative mgh, and I use h to be equals to L into bracket 1 minus cos theta is now equals to the final kinetic energy at this point, which I use as a half mv squared. So directly, my dear student, I can just make V, sorry, formula M get cancelled out. From solving, we can say V is equals to square root of this is square, this is square. So you can say square root of M gets cancelled out. This will be U square minus 2, that's 2gl 1 minus cos theta. So my student should keep this formula in mind directly because it's going to be used to solve a lot of numerical questions. A lot of numerical. So this is just what you need directly. V, that means the velocity, the vertical velocity at which this pendulum drum will move. I get it from what? From this particular point, from the point of rest to this one, to the highest height is given as U square open bracket 2gl open bracket square root of U square minus 2gl by the 1 minus cos theta. You close your bracket. So it's all about formula. So please keep this in mind. For its pendulum board, we use this formula to directly. All this formula I will be quoting there in the numerical aspect of what I told you. The numerical here are just illustrations. There are numerical chapters for which we only solve questions, but we come back to what we have learned in concept. So that is why the concept video is very important. So again, we also talk about another important thing, which I think I need to talk about under this, which we call what? Angular amplitude. Angular amplitude. I will use this same diagram. It's quite rough. And before I do that, I will move this a little bit up. Sorry, guys, it's not me. It is the topic, and we just have to do it the way it's read. So I will not waste your time because I will derive that one from this. So directly, the last one in your syllabus is the one you call angular amplitude. Now, about angular amplitude, we denote that by a Greek letter we call phi. Phi is phi. That's the spelling we call that. Now, to understand that, the body was thrown from this point, a quick recap of what we have studied. It was thrown from this point to this point. I'll be short. Then it will reach its maximum displacement at this point. But when the velocity is 0 at this point, what happens? That something will come back to its initial position. We say amplitude of oscillation is the distance what cover the maximum distance from the starting point, or you said the mean position. This we are going to study under the next chapter of this, which we call simple harmonic motion. They are together, oscillatory and circular motion. So in the next video, we talk more about amplitude. But here, we also want to talk about the angular amplitude. Let's say the body moves from this point, now reaches this particular point, which it has been displaced by. Don't worry, I will use directly because I'm rushing, but we need not to rush. It moves from that point to this point. So let's say the total angle it has covered from that point now is no more theta. We say the total angle at this point from here to here is now taken to that sign I gave you, which we call phi. So when the velocity of the body is 0, the body will come back to its starting point, initial position. So we can talk about angular phi. I said when velocity, the velocity formula we have derived, when velocity is 0, then we have angular. When velocity is 0, we have angular. So when velocity is 0, you can have that, keep that at the back of your mind. So directly you can say, this will give you 0 is equals to under root of, what do you have, guys? U square minus 2GL, open your bracket, 1 minus cos. So this is the formula. Then you can say you square both sides to remove the square. 0 square is still going to give you 0. So you can just collect like times. You have everybody know that U square will be equals to 2GL. I hope students are following. 2GL, open bracket, 1 minus cos phi. I'm using phi and not theta. Sorry about that. So you can try as much as possible to make cos phi solve a formula directly. You can have U square is equals to 2GL. I'm removing the bracket. Then you have minus 2GL cos phi. I hope students are following. So cos phi, which is the angular stuff we are talking about directly, we can say is equals to, directly we can say this is equals to, you can rearrange this one as saying 2GL cos phi. For those that are beginners, I'm trying to keep it simple, is equals to 2GL minus U square. What have I done? I only collect like times. I brought this to the other side. So cos phi will now be equals to, this is 2GL minus U squared over 2GL cos phi. This is the formula we use for that. And this is very important too. As usual, you have to ring it and give it a word. So we can see 1, 2, 3, 4. These are formulas that is important for us to know, to note, and not to make mistake. Then again, we can also, for A-level students, because questions are technical nowadays, you just need to know everything. Now, at this particular point, this point here is kind of rough. You can see the tension of the word. There will be a tension that will act inward. Centripetal force will act outward. The action of centripetal, if I resolve, is also mg what? mv square over r. mv square over r is always centripetal away from the circle. Tension is acting inward. So the total force that will act at that point here, after resolving at this particular point, I'm having something like triangle. You know, you can bring as many formula as you want to bring out. So the total force that will act at that point will be, force acting at that particular point will be, we're talking about the difference between the tension minus the tension minus the centripetal force. The tension which you resolve toward, you can see, I said is the direction of weight is mg cos theta, because this particular force is acting along the tension, and there is what? Another centripetal force acting along that component. Don't worry, on that simple harmonic motion, I'll bring this out for you guys to understand better, but limit yourself to what you have studied for now with respect to your syllabus. But the point I'm trying to make, you get it better on that simple harmonic motion when we talk about the undulating angle. Understand? We talk about that. But at this point, centripetal force is acting outside, and this mv squared by half. Tension of the string is going inward, just like what you have here. Centripetal force is acting here in this direction. Now, in this case, you know, we said for a body, moving in a circular, there will be centripetal force. So the total force acting at this point will now be equals to what? Let's say the tension minus the what? The centripetal force, which is acting along that side, which is given as mv squared by r. So the total force here on a normal day is going to be equals to, you resolve these two components. And when you try to resolve that, I'm going to say along this plane will be equals to what? You have that as what? As cos theta, but you don't need it for that. So that is why I want to talk about it. So this is all for me. And the next thing will be in the next slide, which I think is the next slide. And let's quickly look at that. Wow, this is the last part. Motion of a car around a circular path, talking about the skidding and the turning and the toppling. Wow. So let's be quick to understand. This is just about free body diagram and understanding the constant variable. When a body is moving along a circular path, according to what the student has drawn for us here, now we can understand that something will happen. I love the illustration. Look at the motion. The body is moving along a circular path. Something will happen. Normally, we have studied that what here, there will be a force that will act away from this, which we call centrifugal, mv squared by r. Now it should be balanced by the normal reaction of the body. I love the way you do this, very good. Then remember that what, there's another thing, there's always what, oh, fine. This is a force. The force that is driving this along this. I love this illustration to explain well. Now, as the body is taking a turn, there is what? A force acting in this point. I call it mv squared by r. That is a centrifugal force, not centripetal. What happened? The normal reaction is going, the weight of the car is acting downward as shown. So the force will be, or there will be a force that keep this at equilibrium. So which is called the frictional force, because the body wants to move. Friction will act. Everybody knows. So there are different cases you can always bring out from this one. So what we are trying to say now is that for the body to what? To skid, for normal skidding, for the body to move, the mv squared over r must be less than what? Must be greater than what? The frictional force. So if that one happens, we say mv squared by r must be what? Must be greater than or equals to the frictional force. From here, for equilibrium to set in, we know that what? For static friction, we have talked about that is always equals to mu n. What is n? Normal reaction. Normal reaction is what? Mg. Some of you say mu r. R is equals to mg. This formula for friction. So if from here, the normal reaction balance the weight, weight is equals to mg. Normal reaction is balancing the weight. So what we are trying to say that for frictional force, for skidding, mv squared by r must be greater than or equals to, let's just set equilibrium, must be equals to the frictional force, which is what? Mu n. What is n? Mg. So directly we can say m gets cancelled out. So the normal speed for skidding here must be equals to, I'm making v squared from cross multiplication. We can say mu rg divide mu rg. Am I right? Mu r times g. So we say v is now equals to square root of mu rg. So this is the normal. So you said for the body to skid, for the car to skid, the speed must be what? Must be at this point. So this is what? Speed, skid, speed. So this is very important also for some questions you are going to face under the chapter. So keep it in mind, for a car to skid, this is the way you talk about. So this is the normal safe skidding. The speed should be equals to mu rg, and mu is always equals to coefficient of static friction. V is the speed, r is the radius, the distance at which it is turning, and g is that. Then the other thing which my student told me, those that did jam this, sorry about banked road, banked road, like this. Now this road is banked. The bank road we are talking about, those road that has all this sign. You can see what I'm trying to say, that it is always like this. That is the one they call bank road. So why do they bank road? Is because of safe turning. So keep that at the back of the mind. So for bank road, that means the height of this thing is a little bit raised. So how can a car turn? What is the maximum speed for the car to turn? So this is going to give us another illustration, which you can give different illustration. Now, I will only limit myself to what is required in your syllabus. I won't talk about too many concepts because you might not need them, but you need to understand. And when the road is banked, then you are going to have the angle of repulse, which we've talked about in friction. So understand that carefully. I will need to draw again. So let me just draw, but I will not draw a car because I don't know how to draw a car. So let's see if I can draw a triangle, in particular a right angle triangle. Well, let's see that. I'm waiting for the diagram to come up. This diagram, I don't like it. I'm going to delete. It's like that diagram at all. So let's see. This is one. It's okay. So let's just take some illustration that I think it is cheap. So the road is banked. That is a little bit of height. Then the car will just be, it has now at an angle of theta. The angle of repulse is theta. Remember that. Then we have our illustration time. Excuse me, guys. This is the car now. Normally in classroom, I always draw car for them, but yeah, I'm not drawing any car. So this is the car. I want to turn. This is the road now. So the road has been banked. So it's at a little bit of height. So we want to know the safe turn. And so far, this is banked, my dear. So this is the angle of repulse. It's not angle of friction anyway. Now, here, what we need to understand is still the same. This is the car. Just visualize it like the way you see this car. The road has now been lifted a little bit up. So it has been banked. Then we are looking for the maximum of 20. So in this class, in this one, we have to just give in what the diagram as we have studied. As we have studied that, okay, fine. Which color is suitable for this? Okay, fine. So let's say the weight of this car is acting like this. What is weight? mg. I students know weight very well. The normal reaction, we always balance the weight, which is what I'm trying to draw for you to see very well. So the angle, alternate angle are equal, just for visualization, for you to see. This is what we're talking. The theta here will be equal to the theta here. Everybody know you can balance the angle. Diagram not done to carry. I've actually shifted the point of intersection to this. I can still do that for understanding's sake. Time is far spent. We don't need to be told about that. I think maybe they should intersect. Oh my God. That would be a very bad diagram. Let's say the weight of the body is acting in that point. The normal reaction, I want them to intersect at that point. The normal reaction is acting like this. For visualization, for us to see very well, then the angle is alternate angle, that is theta, right? So let's balance this place for you to see all the forces is acting on it. This is it. The same angle is also here. Different conditions. Don't be afraid. It's what you can do on your own. You can see the way I'm doing it. You can do better. So now you can just resolve component. What happened? Weight is what? mg balanced by normal reaction is n. So this normal reaction will be resolved into two components. That is with respect to this diagram. So everybody know if I'm coming, like, look at it, what is this? Opposite. Outside this, as we have discussed, which force is acting outside the circle? Because it's moving a circular track, is what mv squared by r. My students know that very well. And you know, at the other side, there's a force that is balancing, which we've done in the first illustration that I'm showing here. So now here, we resolve this mv squared by r in two dimensions, in two ways. Then we talk about normal reaction, which we always do. Now, the total normal reaction acting on this thing, you have to be very careful because the overall, there are different normal reactions, it will balance each other. So now I'm resolving this into two components. Watch. In this component here, at the horizontal here, you know, we have opposites over hypotenuse. Opposite over hypotenuse is what? That is sine. Then if I resolve into this component where I have my mv squared here, you can see what I have here is mv squared over r. That is adjacent over hypotenuse. So at this point, we say the force acting here is mv squared over r cos theta, because adjacent over hypotenuse is what? mv squared, that is cos theta. So at this point, look at the vertical force. What is the weight? What is the weight, my dear friend? The weight here is what? mg. So mg is acting along this point. That is mg vertical. opposite over hypotenuse. What's that? That is what? Sine. So that is mg sine theta. So this is the way we illustrate. Then we now start bringing out different cases. So the total normal reaction acting, the overall normal reaction is two forces. The force of what? mv squared, I'll write it out here, mv squared over r cos theta plus, what's the second one? mg sine theta. So this is the way we analyze. You don't need to list. There's nothing here. So we now start bringing out different cases. Case 2, this is case 1. I've talked about safety. When the road is banked, case 2, when we say mv squared over mv squared, this one is equals to this. So we get the what? Situation 1, case 1, you start writing mv squared over r, balance out mg sine theta. What happened, my dear students? That is for a banked road, the first case. What happened? M gets cancelled out as usual. Let's be fast. I say V squared here is equals to RG. Wow. V squared here is equals to RG sine theta. Right? So you can say for safe speed is equals to what? You have a square root of RG sine theta. So what's the difference between the first formula and this? When the road is not bound, it is safe turning. This is mu RG. Here, mu RG is not changing to RG sine theta. Do you understand what I'm saying? So this is the way we talk about that. So, oh, wow. mv squared over r cos theta. I didn't put cos theta. I'm balancing this and this. So that will have screwed this. So this is a v squared cos theta. So let's just finish it. So this, we have v squared cos theta. Sorry about that. Is equals to this. So that should have been what? That's one thing about me. I don't gram. I just need to prove. So what we do here is that we divide both sides by sine theta. Sine theta over cos theta by cos theta rather. You know, by cos theta by cos theta. We've done that before. Sine theta over cos theta is what? Tan theta. So we have v squared equals to rg tan theta. The only difference here is because I know the formula, that's why I know I'm forgetting. So v is now equals to square root of r. What's this, guys? You have rg tan theta. And if you remember from your friction, you know mu. Remember mu. Mu is equals to tan theta. So most of the time, we don't need to waste our time on proving and proving. It's just for us to understand the concept. So you can see that the formula is the same thing. Mu rg tan, and mu is what? Tan theta. So friction cases. So this is the first case, and that is that. Now, the other cases we can bring are, I think for Cambridge students, you can always do that yourself. It's simple. It's not in our own syllabus. But for explanation's sake, the normal reaction that is balancing this thing is mv squared cos theta by r plus mg sine theta. So you can do two cases. If this thing will skid upward, if it will skid upward, it will move upward. That means mv squared over r is greater than what? Is greater than what? Mg sine theta. It will skid upward. The other case is when this thing is skidding downward. When it's skidding downward, mg sine theta is going to work. But one thing you need to know is that this one, the total force acting on this place, if it is skidding upward, is like saying mv squared over r cos theta minus mg sine theta must be equal to the normal reaction on the body. What's the normal reaction? mv squared over r cos theta plus mg sine theta. You can see it will cancel out. You understand? So the cases we are trying to bring out for other cases, which is not in our own syllabus here, is a situation whereby for body to skid upward, and dear students, what happened? This would be greater than this. You get? So keep that at the back of your mind. And for body to skid downward, to move downward, this would be greater than this. So keep that at the back of your mind. Then you can always set the equilibrium of what? Normal reaction to be equals to this. If normal reaction equals to this is the value of normal reaction formula for questions that ask for normal reaction. Normal reaction N is balancing out what? mv squared over r cos theta plus what? mg sine theta. So this also is another important formula you can keep in mind if they ask for the normal reaction of the car that is skidding. The total number of reaction acting on the body is that. So keep it in mind. Please don't make mistake. So this is the only case we are treating with respect to external. Other cases I can bring out. So far I understand this diagram. I can start saying, okay, if it's skid upward, mv square cos theta, mv square by r cos theta will balance this one. If it's skid downward, this will balance this one. Then I cut and bring out my parameter. So you don't need to disturb yourself about getting answers to questions. This is what you need to know. This is where we stop, guys. We are going to look to the simple illustration we always talk about here. These are not the real questions. The real questions are under the numerical playlist on our channel. You can check that. We are uploading gradually. You are going to see all videos with time. So just stay updated. Click on the notification button, and that is how to stay updated. So the last aspect here, guys, is the question on illustration. Illustration, the spelling is wrong. Don't mind the boy, he's tired. That is one. Now we say its velocity is constant, no work is done on the body. It has a constant acceleration directed away from the center. The centripetal force is directed towards the center. Which of the following is true about body moving in constant spin circular? If it is moving in constant spin, that is what we are talking about, uniform circular motion. What happened? Velocity is not constant. Velocity is changing. We've talked about that. It is the speed that is constant. No work is done on the body. Correct. I told you because the force is what? Yeah, your acceleration is equal to what? 0. When body is not accelerating, there is no work done. Fine. It has a constant acceleration, always directed away from the center is wrong. Acceleration is directed inward. Centripetal force is inward. Acceleration is what? Inward. The centripetal force is directed towards the center. It's absolutely correct. So the correct answer here is what? Which one? 2, Roman figure 2, and Roman figure 4. So keep that in mind. That's the question answer. These are basic things that you all can do. The next one I guess is an object of mass 2 kg moves in a circular path of radius this with a speed of this. Calculate the angular velocity. Well, we have learned that v is equals to r omega. Taking angular velocity is omega. Radius, the speed is given as 1 meter. Radius is given as this. So I don't think we are solving anything, as this is going to be useless. So you can see, omega is equals to v divided by, what do you know, guys? The speed is 1 meter moving along a radius of 4.5. The right answer will be 2 radian per second. Like I said, as this word is a question. So I hope you understand. These are basic. I told you these are not questions that we are talking about. The next question is a ball is attached to one end of a string. It moves anti-clockwise around the circle with the center of the circle O. If the same suddenly break when the ball is at one point P, along which of the following path will it move? What is the direction of the velocity of what? Of a circular move? It's always going to be a tangent. I mean, this is not tangent. This is tangent. This is not tangent. This is not tangent. So the answer to this is P, and that is the question. The last but not the least. Time is fast spent. The last question for this slide. The length of the second line of a laboratory clock is 0.1 meter. Calculate the speed at which the tip of the second. Okay, that is because it's rotating in an angular velocity. We know that omega is equals to, you can say directly, v equals to r omega. We are looking for the speed, not the angular speed. So we need to get this. Now it is a clock, and we need to be drawing a simple thing. And you know, if it is a clock, the revolution of a clock is what? 360 degrees. Remember, omega is equals to, say, t is equals to 2 pi divided by omega. And t is equal to inverse proportional to what? 2f. I don't need all these things because I only need to get omega. So if I take omega, I can make omega Sorel formula is equals to 2 pi divided by your dt. So what I'm even saying, even if I don't know this formula, I will get it. How will I get it? It is rotating in a circular path. That is a 360 degree. 2 pi is 360 degree. That is what I'm talking about. So my angular velocity is rotating at 360 degree at every, how many seconds? Every 60 seconds. For the minute to move, the seconds will rotate 60 seconds. So what I'm saying here is that my angular velocity, it is 360 divided by 60. And that will be what? 6. I hope students understand it. For every 60 seconds, this is rotating as what? As this rubbish. That is that. So what I'm saying is, if you want to use this, you say 2 pi divided by omega, no problem. It's okay. And if you want to just do it like a layman, which understand concept, the way I've done it, for every 360 revolution, which is 2 pi, 1 pi is 180, pi radian, pi radian. You know, angles can be in radian and degree. Mathematics student will tell you more. So speed is equals to 0.1 times calculate the speed at the tips of the second. So for every 60 seconds, it's moving at 2 pi divided by 6. You know why I'm using 2 pi? I don't want to use 360. Why? Because answer might be in what? Pi radian. Do you understand? It's from experience. You can say 2 year 1, 2 year what? 30. Do you get? So somebody that says 6 years, 6 times 0.1, 0.6, 0.6 is correct. Radian per seconds, right? Do you understand what I'm saying? If I say V is equals to R is 0.1 multiplied by, this is 360 over 60, that is 6. That's 0.6 radian per second, right? Correct. Absolutely correct. Question answer. You move to the next one, which there's no next one in this one. But here, answer will be in terms of pi radian per second, which is the way you see most of the velocity. So velocity will now be equals to, you can see, guys, 3 year 1, 2 year 30. It is another thing that's saying is 0.1 pi divided by 30. Or 0.1, 1 over 10 divided by 30, that's times 1, that's 1 over 300. So what I'm trying to say is that some questions can be in terms of this. So you can just punch calculator directly, not to waste our time. I have one there. 0.1 divided by 30 is a 3.33333, 3.33 times 10 raised to power 3. So somebody can see this option at 3.333 times 10 raised to power negative 3 pi radian per second. Guys, I am doing this because I know examiner very well. Look at the difference between the answers. Somebody that get the answer 0.6 radian per second will say, no answer there. You are just giving me issues. Nobody is giving you any issue. You are the one that does not understand. This is pi radian. It's term of pi. So which is most time the way you see answer in what in competitive exam. So guys, there I'm going to stop. Don't forget to like and subscribe to the channel and focus on what your strategy. Your strategy is listen to the concept, do numerical questions, have in what notes, short notes in which you put all the formula I always make. Nothing more than that. Knowing physics is not difficult. See you soon. You have a wonderful day. Bye.